Hello and welcome to Data Preprocessing in the Data Mining series. In this presentation, we'll be looking at what is data preprocessing and why it's so important. We'll cover the different types of data preprocessing, cleaning, integration, transformation, and reduction. Data preprocessing is a really important data mining step. Data in the real world is often quite dirty, and data in the academic world can be dirty too. Data can be incomplete, maybe it's missing values, columns. Data can be noisy, where this is where it's recorded on a bad sensor or possibly features human error. And data can be inconsistent. This is where maybe database errors have happened, there's different formats, or data has been measured in different ways. Data preprocessing is so important because if you don't put quality data into your data mining process, you're not going to get quality results out. It's very simple. Garbage in, garbage out. So we really want to put quality data into our data mining processes, into our data mining warehouse. So how do we achieve that? Well, we need to apply data preprocessing. So there's data cleaning. This is where we fill in those missing values. Maybe we need to smooth noisy data to make those points more consistent. Maybe we need to identify and remove outliers where mistakes have been made or unusual edge cases have occurred. And or maybe we need to remove inconsistencies in our cleaning. In data integration, we may need to combine multiple sources of data. Maybe some of the data is spread across multiple databases. Some of the data might be in files. Maybe some data might be spread across the globe and we might have to aggregate it all in one place before we can do our data mining. In data transformation, we'll be normalizing the data and aggregating data. And in data reduction, if we're fortunate to have a data set that is very, very large and contains millions of rows or maybe possibly thousands of rows, or possibly just thousands of rows, we may choose to do some data reduction. And this is where we select rows which will still contain the information of the whole data set, but enable our data mining process to run a lot faster. We'll make a start with data cleaning. Typical tasks in data cleaning are filling in missing values and smoothing the data and removing the outliers. So starting with missing data. So missing data may occur for a number of reasons. Possibly the missing data has occurred due to a malfunction, someone simply not recording it, or missing data maybe have been lost in the storage process, possibly. So to get around this, we may need to infer those values. This means fill in those missing spaces in the data set. Sometimes we can simply go back to the source and fill in those missing values by literally going back and measuring the value related to that particular attribute. However, that's not always possible. Sometimes maybe the opportunity has now passed to collect that data, and we're going to have to do the best we can with what we've got. So we've got several options on the table when it comes to missing data. The simplest option is to simply just ignore that row with the missing value. So maybe it's data about people and you're missing the height for a certain person, and you can just simply delete that entire person from the data set. Now that's all very well if you've got thousands of entries in your data set or millions of entries in your data set. Deleting a few hundred rows may not be a problem. However, if there's a larger percentage of your data set has missing values, then that may cause you to lose a lot of your data. Another way to handle missing data is to make up a value for that, a generic value for that missing data. So for instance, NA, unknown, MISC, trying to come up with some way of labeling that this record has a missing data in it. Another way to handle missing data is to actually fill in that missing value using a mean, for example. You could use a median. We can use this to try and guess what that value would have been based on the other values in that particular column. However, that may not be that accurate, since if the data's got several groups in it, then using the mean may simply just be the middle of all of these different groups, rather than an actual value which is likely for that particular row, or if you like to think about people in a database, that particular person. So one way we can improve the quality of filling in our missing data is we can calculate the mean given based on other attributes in the data. So for instance, what's the mean for lecturers, the mean height for lecturers, and then the mean height for students, for instance. And another way we can fill in the values is to maybe apply a technique like we saw in classification in the last video. For instance, decision trees to try and predict what that value would be. Another challenge we'll come across in data cleaning is noisy data. So with noisy data, we may have a certain amount of unexplained variance in our measurements, and the data points, if you imagine a trend, may be scattered a lot either side of this trend, and that might make it hard to actually spot the true trend in the data. So there's a number of reasons we may end up with data that looks like this. This is data that looks a bit kind of fuzzy. Maybe there's groups in the data in a two-dimensional space, and those groups are a bit fuzzy. That would be described as noisy data. So this can happen because of data entry problems, limits of technology. So maybe the sensor, maybe this is a photography-based data mining task, and the sensor technology isn't that good, and we've got slightly blurry photos. Possibly the data transmission technology wasn't very good that transferred that data, so we had to compress the data down a lot before we could transmit it to where it's stored, and that could cause losses that could then create noise. And noisy data can also occur just simply due to errors and small errors. And for instance, when you're measuring with something like a ruler or some kind of meter or scientific piece of equipment, it's possible, particularly when a human is measuring that equipment, to make small mistakes and end up with data that's either side was not exactly correct, either side of that trend, or slightly outside the exact groups that we're expecting to see. So how do we handle noisy data? One approach is the binning method, though that's not chucking the data in the bin, although that may be tempting when you do have noisy data. The binning method is where we partition the data into bins. These bins can then help us with smoothing. Another approach is applying clustering. We'll go into clustering more in the future, but essentially this is when we cluster the data into groups, and then things that fall outside of those groups, a few points may fall outside of those groups, and we can consider those points either noise or outliers. We can also just manually look at the data and try and inspect the data and spot outliers. Some outliers are very obvious and maybe very explainable. This is when the machine went into that state when it was measuring this, and anything above 10 is definitely nonsense. Or maybe that's when their hand was in the way of a certain sensor. Another way we can smooth data is through regression. So we can try and get a trend from the data, and then either use that model or see how far certain data points are from our model, and then count them as outliers this way. So in the binning methods we're now covering, there's essentially two different ways of creating bins. One is equal width. This is where we divide the partitions into groups that are of equal size. So for instance, we would go 10 to 20, 20 to 30, 30 to 40, and so on. The other way of creating those bins is to use an equal depth policy. This is where we put the same number of data points into each bin. We'll sort our data. We'll take the first 10 points and put them into that bin, the next 10 points and put them into that bin. The ranges of the data we're now allowed to be flexible. So with the equal width, we may have many points in the range 10 to 20 and not so many points in the range 20 to 30. And then with your equal depth bins, you'll always have 10 rows in each of your bins, but your bins therefore won't necessarily span a consistent gap anymore. So here's an example of those binning methods. So if we had that data up the top there, for instance, this is a price in dollars. So we've got everything from $4 up to $34, and that's already been conveniently sorted for us in order. Let's say we want to partition into equal depth bins. we're going to break that up into groups of 4, for instance. So we take the first 4, put that into bin 1, the next 4, put that into bin 2, and the next 4, and put that into bin 3. We could then applying a smoothing function. So maybe we wish to smooth by the bin means. So we can then calculate the mean of those numbers. So we can sum 4, 8, 9, and 15 and divide by 4 and get a mean of 9. And the same again for bin 2 and bin 3. Another way we can smooth is by bin boundaries. Each bin value is replaced by the closest boundary value to that particular value. So we've got the bin boundary on the bottom. Some of those numbers were closer to 4 than they were to 15. And on the other side, on the next one, some of the first 2 values in bin 2 were closer to 21 than they were to 25. And same again in bin 3. So instead of binning the data, another way is to use cluster analysis. So clustering is an unsupervised learning technique. And here on this graphic, you can see that this, I think this algorithm looks like DV-scan. This particular clustering algorithm has recognized 3 clusters, the green, the yellow, and the red. It has also recognized the outliers. So you can see those black points there that are outside of those 3 clusters. They're not close enough to be within the density range of those clusters. So those points are not in, those black points are not inside those clusters, and we can infer that they are indeed outliers. There's also traditional outlier detection algorithms. These can remove noise and outliers from data sets. And one of my favorites is the local outlier factor. This is a density-based approach, and you can see that, other hand, here on the right of your screen. And that is a technique which looks at the neighborhood around the point and sees how hard it is for it to reach other points. Points that are in an area of quite low density can be considered outliers, and obviously points that are in an area of high density can be considered not outliers. But what's nice about the local outlier factor is that it gives you a measure of outlierness. So some of those points are more outlying than others. So that could represent that in this graphics by using a graduation of color instead, fading from orange to blue, but they haven't. The simplest approach, of course, for outlier detection is simply just to calculate your interquartile ranges and remove everything outside of a given percentile. So you might remove everything beyond the 5th and the 95th, outside of the 5th and 95th percentile of the data, chop those bits off, or maybe the 25th and the 75th percentile, and chop those bits off. That's obviously the most simplest approach of moving outliers. As I mentioned earlier, regression can be used. So we've plotted a trend line here, and we could either simply use that trend line to represent this data moving forwards, or we could look at the distance of different points from that trend line to detect our outliers. So next we'll talk about data integration. This is where we combine data from multiple sources into one coherent store. We may come across certain problems when we're doing this. So for instance, we might end up with duplicated data. So maybe a customer has set themselves up on a global and a regional version of a company, maybe they're a customer to both the global and the UK branch of the company. And then when we combine those data sources, we end up with duplicate customer records. So that's one problem that could potentially arise. Another problem which can come from combining multiple data sources in particular databases is clashes of IDs. So if both systems are counting from one in increments of 1, and another system in another region is counting in increments of 1, if we just simply combine those data sets, we'll end up with a duplication of keys. So we can't may no longer be able to identify records related to those records in other tables in the databases. So when we combine our data sets, we may end up with redundant data. So this is a duplicate data where we've got the same person twice in the database, or we've got the same measurement, same measurement effectively taken twice in 2 different forms. So for one example this slide gives here is an attribute derived from another attribute. So we may have a case of duplicated data or something measured in two different ways where those measurements are very, very similar. So it's very important to be careful when we combine multiple data sources to avoid these redundancies and inconsistencies. A technique for detecting if we've got a duplication or redundant data in our data set is to look at correlational analysis. So this is the Pearson correlational coefficient. And we can use this to compare two columns with one another and see how much they correlate. The correlational coefficient is around 1 if x and y, our two columns, are independent of each other. So there's no real trend between the two columns. So in that case, they're completely unique, and they're not a copy of each other at all. Then there's a possibility that they have a positive trend. So in this case, the correlational coefficient, Pearson's correlational coefficient, will be it'll be 1 if they're all perfectly aligned. In other words, they're exactly the same, increasing in exactly the same amount. Or the correlational coefficient can be less than 0, which would imply a negative correlation. So I'll show an example of how to work this out in Excel.
This is an example of calculating the Pearson correlation coefficient in Excel, manually that is. So here we have the formula for Pearson's correlation coefficient, and up here we have our data set with our x and our y column. So in our x column we've got 3, 6, 9, 12, and in our y column we've got 9, 2, 1, 1. We can see in this case we've got a negative correlation. So as x increases, y generally tends to decrease. So the first step of following this formula is to calculate those means. So we've got the x with a little with the line above it there denotes the mean. So we've calculated the means of these two columns. Then we calculate this x term here. So we've got x minus the mean. So each row of x minus the mean of the x column, and that's taken care of here in the Excel spreadsheet. So we're taking the value for x, and we're deducting its mean for that whole column, and we're doing the same thing again for the y term. These values are then times together. The x and the y are then times together. You can see this here in the formula, with these two terms being next to one another. In our formulas, we don't put the time symbol in, or an asterisk. We just by virtue of them being next to one another, we know to multiply them. These values are then summed up. So you can see this sigma here, and the sum here in the Excel spreadsheet. Now for the bottom of this fraction, we have the x value, the x term squared. So we've times it by itself here in our spreadsheet, and we have the y value squared here in the spreadsheet as well. We then, just like we did before, we sum up those values, except we don't do any multiplication this time. We just got the y term summed up, that's that one here, and the x term summed up, that's that one here. We then do a square root. That's taken care of by this cell here, so we've got the square root function in Excel, and again for the y term, the square root. We then multiply those two terms together, those two square root terms together. Finally, we do the division of this whole fraction here in the formula, and that gives us, as we was expecting, a negative value, representing that negative correlation. And we could change this to be positively correlated with the thing, and we should see that value turn to a positive value. So I'll quickly just delete these values and put in some values that represent a positive correlation. So 5, 6, 7, 10, 15, and you can see now we've got a positive value in this cell here of 0.9. So showing that these two columns are now positively correlated together. Now if I randomly generated these two columns, we would hopefully see a value around 0. hopefully that makes sense, and you now know how to calculate the Pearson correlation coefficient in Excel, and I'm confident you could figure out how to do it by hand as well based on this, by following those steps manually.
So as I mentioned just before, this is just a visualization of graphic to help you understand how the coefficient works. So at the very top there, you can see that the correlation, if it's the coefficient will be less than 0. If there's a negative correlation, it'll be around 0 if there's no correlation, and it'll be greater than 0 if there's a positive correlation between those two attributes, x and y, those two columns, x and y in this case. So next we'll talk about data transformation. Data transformation is a very important step. The biggest part of data transformation is normalization. So we've touched on the importance of normalization for clustering algorithms. So normalization is where we place all of our data between the same scale. So for instance, between 0 and 1. It's simple to do this. We can look at the range of the data and then divide our data to fit between that range. This is really handy for clustering and classification algorithms, seeing as these can be thrown off by differences in the scale of different columns. So for instance, if the one column was on a very large scale and one column was on a very small scale, the classification clustering algorithms some classification and clustering algorithms will be thrown off by the difference in scale and pay more attention to the column which has the greater difference in scale. In data transformation, we may combine values, extrapolate data to create new columns, or even combine columns and aggregate data. Or we may summarize data. We may put our data into a data cube and apply different levels of aggregation to it. Starting with normalization, probably the most important data transformation technique. So here you can see that example I was talking about, where we are putting the data between the range of 0 and 1. So we take those house prices, for instance. It looks like, oh, maybe not house prices, possibly, well, these amounts of money anyway. And we look at the range of this data such that the smallest value will be represented by 0, and the largest value will be represented by 1, and everything else in between will be between 1 and 0. So next, let's talk about data reduction. And in data reduction, we are talking about, we're in the fortunate position of having a lot of data. I mean, you could also say that this is an unfortunate position as well, as it may be very tricky to handle with your conventional data mining tools. You may need to adopt a big data techniques and use unconventional tools. So data reduction is very important when we've got terabytes, gigabytes, petabytes of data, and we apply machine learning to it. And this could take a very long, certain algorithms can take a very long time to execute on large data. Maybe the actual time they can take can actually increase exponentially with the size of the data set. So some algorithms, the amount of time that they take to run increases linearly with the size of the data set. The more rows you add, the longer it takes. Very simple, but some data mining algorithms increase exponentially. So the more rows you add, the harder and harder and harder it gets to run the algorithm, to the point where it becomes computationally infeasible, or you need a huge cluster computer that you may not have access to. We can apply data reduction techniques to get around this. The goal of data reduction techniques is to reduce the size of the data while retaining the information in that data. So what do I mean? I mean, keeping the model that is inside that data, keeping the trends, keeping the information, keeping the shape of the data intact, but reducing the number of data points in that data. There's also the other way of reducing the size of the data. That's to reduce the number of columns in data. So in this case, we'll be looking at which columns are least beneficial and removing those, or possibly combining columns that are least beneficial to make new columns. Oh, and the other way of reducing data is actually to simplify the actual number of values in our columns without necessarily reducing the number of rows. So this is where we use less data to represent the particular values. So you may be aware some computers are 64-bit and some computers are 32-bit. And if you have some really old gaming consoles like I do, like a Sega Mega Drive, that's a 16-bit. And of course, the largest number that the system can represent is limited by that the bit width of the CPU. So the Sega Mega Drive can only the largest number it can represent is 2 to the power of 16 in binary. So we have 16s, 1s, and 0s to play with, to create our decimal numbers with. In a 64-bit machine, we have a lot more 1s and 0s to play with to create our decimal numbers. Lots more 1s and 0s in binary to create our decimal numbers, I should say. So, but for instance, in a data set, say that we have a 32-bit number representing age, for instance, but we could actually reduce this down to use fewer ranges. So we could then just use many fewer bits to represent the values. We'd have just 4 categories or 6 categories, and we could represent that with fewer 1s and 0s. We could, maybe if the values of age were under, we could use a byte data type to represent the age, for instance, saying it always be under 255 and positive. So starting off talking in detail about row reduction. So there's 2 different types. They're kind of hidden behind me right now on the PowerPoint. You may have to look at this here without me here. I'll put the PDF up on the Canvas site. So there's parametric and non-parametric methods. There's parametric and non-parametric methods of lots of things, but what they essentially mean, parametric means that we assume that the data fits some kind of model, and non-parametric means that we don't assume anything. So with a parametric model, we might assume that the data is in spherical Gaussian distributions. We might assume that there's that the blobs of data are roughly spherical. But in a non-parametric method, we wouldn't make any such assumption. So there's sampling is a technique, is the most common technique for reducing the number of rows in a data set. We might just do a simple non-parametric approach to sampling, where we simply just randomly sample the data set. In this case, we're not assuming that there's any model in a data set at all. Another way of sampling is maybe we cluster the data first and then we do a stratified sampling. But in this case, we're assuming a model. We're running that clustering first. We're looking for those groups of data. In sampling, in simple random sampling, where we're just taking a random sample of the data, there's 2 different techniques. There's simple random sampling without replacement, and there's simple random sampling with replacement. So in a simple random sampling with replacement, we may get duplications of our data. So on the left side of the screen here, there we go. We have 1 to 5 in our data set, and then above me we have we can see that 2 has been duplicated, so it's been sampled twice. Think of it as in a bag of marbles where we take out a random marble each time. We look at it, we write that down, and then we put it back. With simple random sampling without replacement, we take the marble out of the bag, we take that row of data, and then once we've sampled, we've noted down the value, we then leave that outside the bag, and then we take another marble, and then we see what that is. And so we don't end up with any duplication. So you can see above me we've got 2, 5, 4. It wasn't possible to take the 2 a second time. So as I mentioned earlier, clustering can be used to reduce the size of the data. So there's 2 ways this can happen. So we could actually cluster the data and then just save the information that describes those clusters. So if we assume that our data is in 2 Gaussian distributions, we can take those centroids, and we can take their location and their deviation, or their mu and their sigma values, and we can get that. We can basically draw that circle around there and understand how faded out those points are, and we can just use that instead to do calculations on. So to make an approximation based on a much smaller amount of data, rather than having all of those data points. So, and the other way of using clustering is for a stratified sample. So in this case, we do the clustering just as before, but this time we use those clusters to take a fair amount of points each time to represent those different clusters. So we've got 2 clusters there, and then we've been able to take 5 or 6 points. They should probably be equal. Maybe 2 of the green ones on top of one another. And so that way we take a sample, we make sure that we include every cluster in our sample, so we don't miss any clusters. Because, for instance, say we had 20 clusters, and we were taking a 500, or maybe slightly less, maybe 300. We're taking a sample of a data set that had thousands of points. We're just taking a sample of 300 points. It's possible that we could actually entirely miss a cluster and not take any points at all from it. It's a risk with that simple random sampling that we showed earlier. So whereas with the clustering, first, and then do a stratified sample and make sure they don't miss any of those clusters of data. So now moving on to aggregation for our data reduction. So we can aggregate our data in lots of different ways. There's lots of different functions we can use to aggregate our data. Maybe we're counting frequency, we're doing summation, we're looking at averages. So we can aggregate on different levels for different, depending on the type of analysis that the decision makers are looking for. So we've talked about this in the data warehousing video, so I won't go into too much detail here. So now moving on from reducing the number of rows to reducing the complexity of the data, down to reducing the number of columns in the data, the number of dimensions. So sometimes you may have really high dimensional data. Maybe you've got data from a number of medical tests and some survey values, and you've got data that's, for instance, 30 dimensional. You've got maybe 30 questions and maybe 10 measurements. So you've got a large number of columns, but do you need all these columns? These columns can cause problems. For instance, the columns can, I think there's a thing called the curse of dimensionality. So the more dimensions we add to the data, some clustering and classification algorithms perform worse the more dimensions there are. So it's important to control the number of dimensions we present our machine learning algorithm with, and it's important to make sure that all of our columns have meaning. So there may be columns that have no bearing on what we're trying to classify or predict. So, for instance, favorite color may have no bearing on whether or not you're going to get type 2 diabetes when you're older. So there's different approaches we could use to select these columns. There's the forward selection, there's backward selection, and then there's something in between those two types. So in the right side here, the combination of the two forwards and backwards techniques. So in the step forward selection, we are taking the best column each time and adding that to our data set, and then looking again at our remaining columns and seeing which one of those is now best or contains the most information, and take that column. In a stepwise backward elimination, we're removing the columns which that contribute the least to the data set. That's the least information. So you may remember when we was doing the decision tree, we talked a little bit about information theory and entropy, and the amount of And just like as we was doing then, we can calculate the amount of value in a column. So in this case, we're going to remove the columns that add the least to the data set, and then recalculate again and see which one now is the worst, and so on, until we have a suitable number of columns. And then there's a mixture of the two. Another way of reducing, this is not reducing the number of columns this time actually. This is reducing the number of data rows actually. Histograms are for, we put our data into bins, similar to as we saw with the binning, and then we can calculate different, we can aggregate the data, and we can calculate different, we can essentially summarize all of those data points with a single value. So unlike before where we were using the binning for smoothing, in histograms we're using the binning just to capture one value from those group of values. So for instance, we just calculate the mean and we use that to represent that particular bar. Or when we more typically use it when you're calculating the frequency of something. So here, this very colourful chart behind me here is showing the histogram of arrivals. Maybe this is to a shop, maybe, or to an airport possibly, and probably a bit low for an airport. I think it's a shop, I think, and we can see the number of people coming in over different hours of the day. So we can see that they seem to have a peak somewhere in the middle of the day, about 4 o'clock, and this is but rather though all those rows of data there are maybe surveys that were conducted with all those customers that come into the shop, but now we're just going to represent simply the number of people that come into the shop, and that can be useful. Now we can see a trend of when the most common time, when the worst time to go shopping is in this case. Another way of reducing so this is not reducing the rows or the columns of our data, this is reducing the complexity. We kind of touched on this slightly a few slides ago when we're talking about reducing the size of the numbers, the complexity of those numbers. So here we've got the age, and this is an example from one of the previous slides, in fact. And you can see here that in the age column, you may have not noticed it, but of course age is actually really a numeric, best represented by a numeric value. But to reduce the complexity of the data and to make it actually, in fact, make it suitable for our classification algorithms as well that we applied in the classification video, we simplified that numeric value down into a set of concepts, into a set of higher level concepts. So rather than capturing their exact age now, we just capture the age bracket that they're within. This will also be handy for privacy as well, from point of view of reinforcing the anonymity of data, thinking about the age data in this example. So some data columns of data values lend themselves to a hierarchy. So in our data cubes, we talked about this a bit in the sense of addresses and maybe locations of sales. So you could generalize the data by a country, by district, by postcode, and so on. But you can generate those hierarchies automatically. So for instance, we have sales in certain counties and in certain towns, and we can get the computer to generate those hierarchies for us. So we won't have a list of all of the counties. We'll just have the counties that we have data for and the towns we have data for. So and you can see actually there's lots of examples of hierarchical data in existence. So even things like postcodes have meaning. So all the different parts of the postcode narrow down exactly where that property is. So it's possible to apply these concept hierarchies in lots of different places. Another technique for reducing the complexity of data in a similar way is by natural partitioning. So we can break our data down into ranges, and just like we did with the age value there's a rule that we can apply to come up with these ranges, so we don't have to choose them arbitrarily, and we can apply some kind of technique, some kind of scientific technique to producing them, and make it as easy as possible for our analysis and our graphs, for creating our graphs. And this handy rule is the 3-4-5 rule. So if a interval, if our data covers 3, 6, 7, or 9 distinct values at the most significant digit, then we partition the range into 3 equal width intervals. Similarly for 4 now, so if it covers 2, 4, or 8 distinct values at the most significant digit, then we can partition it into 4 equal width intervals. And then lastly for 5, if that column covers 5 different distinct values at the most significant digit, then sorry, if it covers 1, 5, or 10 distinct values at the most significant digit, then we should break that range into 5 intervals. I'll just give a quick example of how that would work. This is the simplest case, so some ages spanning from 20 to about 50. And we can see that there's 3 different values for the most significant digit. So we've got 2, 3, and 4, i.e., 20, 30, and 40. People in their 20s, people in their 30s, and people in their 40s. So with that, so we've got 3. Our range covers 3 digits at the most significant digit. So we're now going to break that up into 3 ranges. So in this case, it's very simple. It's very clear. We create a range of 20 to 30, 30 to 40, and 40 to 50. And those numbers divide nicely so that you can create even groups, equal width groups. So as with 10, if you broke 10 down into 5 groups, you'd be doing it every 2. And you see those numbers make it easy. So today we've talked about data pre-processing, a very important issue for data mining and warehousing. And it does make up quite a lot of the work in a data mining role. And hopefully you've got a better understanding of data cleaning, data integration, and data transformation, and data reduction. So thank you very much for your attention today. There's no required reading for this week. There's quite a lot of reading last week. We have covered most of the areas that the book covers for data pre-processing. If you're interested, there is a chapter on data pre-processing that you can review. Although we have covered enough of the ground in this presentation, so you don't need to worry. So thank you very much for your attention, and I hope you have a lovely afternoon. And please join us in the lecture as well, the live lecture. Thank you very much, if you can.